like standard fare oxidation number stuff, like from general chemistry, organic chemistry. We did them back in the first semester, organic. So this is actually the answer right here. We're doing B here. So we have metal, then we have CO, that's the carbon monoxide again, right? And then we have 3 of those. And then what we have is PPH3. And so those PPH3, those were those Wittig reagent, phosphorus with 3 phenols that you may have seen or remember. Oh, we looked at them before in the lecture, so you can go back in the lecture. And so these are each going to give you 2 electrons for this complex right here, this structure. And again, that PPH3 is one structure. One of the things you can know that by is that like phosphorus would not be able to be by itself, right? There just would not be able to be any sort of phosphorus that can be by itself. Yeah. So those have to be attached to the phosphorus. Yeah. If you forgot everything else. Remember that most of these structures have to have internal rules within them that are the same organic and general chemistry rules as we always had. So like you can actually check your own work over and over and over within this same structure. So right here we see that we have a negative charge. And so these are neutral, right? We don't have to have any charges for those. And so what we end up seeing is the metal here has to have a negative charge, actually. Okay. Now, this is kind of a weird thing. Your general chemistry and organic chemistry bells are probably ringing off going, oh my goodness, we have a negative metal. But this is entirely possible when you have ligands on it, right? Because the ligands are going to pull that negative charge out. So yeah, the oxidation state is negative on the middle, but that's because the ligands are all pulling them in every direction. Okay? And sharing that charge. All right, so what we're going to do then is this is going to have 18 total electrons, right? 2 electrons each for each of these things, because none of these is a multiple hapticity, right? They're all singular. Okay? And the kind of easy way to know that is that this all comes to a point, doesn't it? In case you forgot what that was. Okay? If it comes down to a singular point, then it has to have 2 electrons in it. That has to be giving 2 electrons to the structure.
Why would it be positive? I've still got the right answer somehow.
What do you mean positive?
The metal. So doesn't
the metal's not positive. The metal's negative.
I know, but so the last one, it's hydrogen was negative, so the metal.
So we'll total up 8, right? The metal's going to have 10 electrons. And so you'd go to 10, right? And then what you're going to do is you're going to shift 1 to the left because you had gained an electron. It's negative.
So there's gain an electron.
Yeah. So it had gained an electron. It's negative. So instead of being 10, you're going to be 9, which is CO. We shifted last time the other way.
Yeah.
So instead of looking for 6, we looked for 7 electron valence. Yeah. See that? So here we're looking for 9 electron valence.
So how did we know that the metal?
That charge right there.
Oh, I thought that was saying that the Wittig reagent thing.
No, that's not negative. Yeah. Nope, that's the overall charge. Okay. Anybody have any questions? All right, I'll let you try the other ones. This is one of the homework problems. So. Did 2 of them for you. You guys do the others. All right. Does anybody have any questions on that? Okay, so practice. If you still are not sure you understand this, you can actually, the next one past this, same stuff. So 12.1 and 12.2 is the exact same problem, just different ones you're doing. And there's also some examples in your text. Once you start getting it, you're going to go, oh, this was kind of, this was a lot easier than I thought. But, you know, it's like anything else. You got to get the tricks, right?